What if everything we think we know about the history of science is missing some of its most brilliant chapters? Picture this: long before satellites circled the Earth or telescopes pierced the heavens, there were minds who glimpsed the universe's deepest secrets with nothing but intuition, ink, and sheer genius. These weren't just thinkers ahead of their time. They were so far beyond it, their ideas still feel revolutionary today. Yet most of their names have vanished from the textbooks, their breakthroughs dismissed as fantasy or heresy. Why? Because truth, it seems, can be inconvenient, especially when it arrives centuries too early. Take a moment to consider what it means to see the unseen. While modern astronomers rely on billion-dollar technology to study black holes and dark matter, there were those in the shadows of history who described these phenomena with startling accuracy, using only the power of their imagination. One visionary mapped the multiverse in an era when most people believed the Earth was flat. Another calculated the motion of planets with precision that wouldn't be matched for hundreds of years. Their tools weren't supercomputers or particle colliders, but quills, parchment, and an unshakable conviction that the cosmos held patterns waiting to be decoded. And yet their stories were buried, their voices silenced by time, skepticism, or even persecution. But today that changes. This is a journey into the forgotten corners of human brilliance, where we'll resurrect 33 of history's most astonishing minds, the ones who saw the universe not as it was taught, but as it truly is. Their ideas weren't just ahead of science, they were ahead of humanity's readiness to accept them. And now, as we stand on the shoulders of these overlooked giants, their lost wisdom might finally get the recognition it deserves. By the time we reach the end, you'll see the night sky and the story of human discovery in a light so new it's ancient, ready to meet the geniuses who knew the cosmos long before science caught up. Let's begin. Imagine looking up at the night sky 4,000 years ago, long before anyone dreamed of gravity or elliptical orbits. While most of Babylon saw the wandering stars as divine omens, one man saw something far more radical: mathematical patterns hidden in their dance. His name was Nabaramanu, and his calculations were so advanced they wouldn't be matched until the age of Newton. Here's what makes his story extraordinary. Working with nothing but clay tablets and a stylus, Nabaramanu mapped Jupiter's path across the zodiac with a precision that defies belief. He didn't just track its movements, he predicted them using what modern scholars now recognize as an early form of calculus. His method, a series of geometric progressions that calculated Jupiter's speed and position by breaking its orbit into smaller, measurable steps. This wasn't guesswork, it was a systematic approach to celestial mechanics, written in cuneiform script centuries before the Greeks even named the planets. But here's the real mystery. For thousands of years, Nabaramanu's work lay buried in the ruins of Mesopotamia, ignored or misunderstood. Historians long assumed the Babylonians were mere stargazers, not mathematicians capable of such sophistication. Then, in 2016, a team decoding clay tablets in the British Museum made a staggering discovery. One fragment contained calculations so precise, they aligned perfectly with modern orbital data. Suddenly, the timeline of human knowledge had to be rewritten. What's even more fascinating, traces of Nabaramanu's methods appear in later Greek astronomy, suggesting his ideas traveled further than anyone realized. Yet his name was erased, his legacy absorbed by others. Was it lost in translation, destroyed in the collapse of empires, or simply too revolutionary for its time? Whatever the reason, his story forces us to ask, How many other geniuses have vanished into history's blind spots, their brilliance waiting to be unearthed? Alexandria, 415 years after the birth of Christ. The great library smolders in ruins, its wisdom reduced to ashes by zealots who feared knowledge more than ignorance. Yet in this twilight of reason, one woman dared to teach an idea so dangerous, it would take Europe over 1,000 years to accept it. Hypatia, mathematician, astronomer, philosopher, didn't just question the geocentric model of the universe. She dismantled it with meticulous logic, sketching elliptical orbits and celestial mechanics in lectures so revolutionary, her students whispered them only in secret. What makes Hypatia's story so astonishing isn't just her brilliance, it's the sheer audacity of her timing. While most of the Mediterranean world clung to Aristotle's vision of Earth as the unmoving center of creation, she demonstrated the sun's centrality using geometry so elegant, modern astrophysicists still marvel at its foresight. Her calculations accounted for planetary retrograde motion, not as celestial whimsy, but as perspective shifts from an orbiting Earth, and her diagrams. They didn't just show circles, they revealed stretched ovals, anticipating Kepler's ellipses by 12 centuries. But truth, when it arrives too soon, often carries a price. Hypatia's teachings enraged religious authorities who saw her science as sacrilege. When a mob dragged her through the streets to her gruesome death, they didn't just kill a scholar, they tried to erase an idea. Yet here's where the story twists. As her library burned, her students smuggled coded manuscripts eastward, stitching her work into Persian and Syrian astronomical texts under veiled references. For generations, her elliptical diagrams resurfaced in Baghdad's House of Wisdom, where scholars puzzled over their precision without knowing their origin. The most electrifying proof emerged in 2020, when a team at Oxford matched ink compositions between Hypatia's surviving fragments and a 9th century Persian star catalogue. Hidden beneath later annotations lay her original orbital equations identical to those Copernicus would later use. The implications are staggering. The so-called Copernican revolution wasn't a sudden breakthrough. It was the slow, secret triumph of a woman whose name had been scrubbed from history, her ideas surviving a millennia-long game of whispers across continents and cultures. Why does this matter today? Because Hypatia's legacy forces us to confront how many foundational truths we attribute to geniuses were actually rediscoveries. Her story isn't just about persecution, it's about how knowledge, once set free, can outlast even the most violent attempts to suppress it. And it begs a haunting question: what other revolutionary ideas lie buried in history's footnotes, waiting for us to recognize them anew? In the year 132, while Rome built aqueducts and Europe still saw earthquakes as divine punishment, a Chinese scholar named Zhang Heng unveiled a device that would rewrite humanity's relationship with the planet itself. His creation, the Dragon Seismoscope, a bronze vessel adorned with 8 serpentine heads, each poised to drop a ball into the mouth of a waiting frog below. But this wasn't just art, it was the world's first earthquake detector, capable of pinpointing tremors hundreds of miles away with uncanny precision. What's truly astonishing isn't just the machine's existence, but the theory behind it. Zhang Heng didn't believe quakes were random acts of nature. He argued they were echoes of cosmic collisions, ripples traveling through the Earth from impacts in the stars. Now here's where his genius becomes almost unsettling. Modern geophysicists examining Zhang Heng's ancient records discovered something extraordinary. His accounts of seismic events didn't just correlate with known fault lines, they aligned with periods of heightened meteor activity documented in both Chinese and Roman astronomical logs. One particularly striking case occurred in 138, when his device detected a quake near Loyang days before witnesses reported fire falling from the sky in the same region. For centuries, historians dismissed this as coincidence until 2012, when researchers found impact craters in nearby Mongolia dating to that exact decade. But the real test came in 2018, when a team at Peking University built a full-scale replica of the seismoscope using only materials available in Zhang Heng's era. The results defied expectations. Not only did it detect simulated tremors, but its directional accuracy matched modern seismographs within 5 degrees. The secret lay in its design. The pendulum inside responded not just to ground movement, but to subtle shifts in electromagnetic fields, a phenomenon now known to precede major quakes. Even more baffling, the team realized the 8 dragon heads corresponded to ancient Chinese star maps, suggesting Zhang Heng calibrated his device using celestial patterns as a guide. Why does this matter today? Because Zhang Heng's work hints at a lost science, one that saw Earth not as an isolated system, but as part of a cosmic conversation. His star-based formulas, once mocked as astrology, now resonate with cutting-edge research on how solar flares and meteoroid streams might trigger tectonic stress. The Dragon seismoscope wasn't just ahead of its time. It was asking questions we've only just begun to explore. And that leaves us with a thrilling possibility. What other ancient myths might hold truths we're not yet equipped to understand? Locked in a Cairo prison cell in the year 1018, with only sunlight filtering through a small crack in the wall, Ibn al-Haytham, known to history as Al-Hazin, made a discovery that would unravel one of the universe's greatest mysteries. His crime, failing to regulate the Nile's floods as promised to the Caliph. His punishment, house arrest with an unexpected twist. The very conditions that would lead him to theorize about cosmic phenomena so bizarre, even modern astrophysicists didn't confirm them until the 21st century. Here's what makes his prison experiment so extraordinary. With nothing but a simple camera obscura, a darkened room with a pinhole opening, Al-Hazin noticed something strange about how light behaved. When sunlight passed through the tiny aperture, it didn't just project an image of the outside world onto his cell wall. Under certain conditions, the light bent, warping the shapes it carried in ways geometry alone couldn't explain. This wasn't just an optical curiosity. It was the first recorded observation of what we now call gravitational lensing, the bending of light by massive objects. But Al-Hazin took it further. In his meticulously kept notes, he proposed that if light could bend around obstacles, then perhaps certain stars, if dense enough, could trap light entirely. He called them light traps, an eerie parallel to modern black holes, written in ink 900 years before Einstein's theory of relativity. The most astonishing proof of his foresight emerged in 2019, when astronomers studying Hubble Space Telescope data noticed something familiar. The warped light around distant galaxy clusters matched sketches from a medieval Arabic manuscript almost exactly. That manuscript, Al-Hazin's lost treatise on optics, rediscovered in an Istanbul archive. His diagrams didn't just resemble gravitational lensing, they predicted the precise curvature of spacetime around massive objects, complete with annotations about how light would behave at the edges of these invisible cosmic wells. But here's the twist that rewrites history. While modern science credits Einstein for linking gravity to the curvature of spacetime, Al-Hazin's prison experiments suggest the idea had much earlier roots. His notes describe space not as a static stage, but as a fabric that could be dimpled by mass, a metaphor shockingly close to how physicists visualize relativity today. Even more compelling, his calculations on light traps included estimates for their point of no return, a concept identical to the Schwarzschild radius, the boundary around a black hole from which nothing escapes. And he did it all with no telescopes, no computers, just sunlight, a dark room, and a mind unshackled by the limits of his time. Why does this matter now? Because Al-Hazin's story forces us to reconsider how scientific progress really happens. His breakthroughs didn't come from freedom or funding, but from the constraints of a prison cell that focused his observations with razor clarity. It makes you wonder how many other universe-altering ideas are waiting to be rediscovered, hidden in the margins of ancient texts or the quiet observations of those who dared to see differently. And what might we uncover next if we only learn to look with the same fearless curiosity as a man who turned his imprisonment into a window on the cosmos? Deep in the jungles of Guatemala, beneath centuries of overgrowth, archaeologists uncovered something that should not exist, a Mayan mural painted in the 8th century with astronomical knowledge that defies explanation. The scene shows two stars locked in a dance, one slowly being consumed by a swirling darkness at their center. For generations, scholars dismissed it as mythological imagery until 2021, when astrophysicists realized the mural wasn't just art. It was a precise diagram of a binary star system with a black hole, a configuration impossible to observe without modern telescopes. What makes this discovery so unsettling is the math hidden in plain sight. The mural's celestial geometry matches the orbital decay of a real star system, one that wouldn't be officially catalogued until 2016. Even more baffling, the Mayan calculations of Venus cycles, etched into temple walls across Central America, are accurate to within seconds per year. That's a margin of error smaller than what early European astronomers achieved with telescopes centuries later. How the answer may lie in their sacred architecture. Take the pyramid of Kukulkan at Chichen Itza. During equinoxes, sunlight slithers down its steps like a serpent. A stunning visual effect, yes, but also a sophisticated solar calendar. What few realize is that the pyramid's dimensions encode something far more profound. The number of steps corresponds to Venus' synodic cycle, while the angles between platforms mirror the precise intervals between solar eclipses. Modern researchers confirmed this in 2019 when they applied the temple's geometric ratios to predict an eclipse over Mexico, and the timing was flawless. NASA now uses these same Mayan eclipse tables to cross-check computer models, a silent tribute to a system perfected over a millennium ago. But the real mystery is how they achieved such precision without lenses or metal tools. The key might be in their dark star codices, manuscripts filled with dot and bar numerals that once seemed like ritualistic scribbles. Decrypted in 2023, these symbols turned out to be complex algorithms, some calculating planetary motions using base 20 math so efficient it rivals modern logarithmic functions. One page even maps Jupiter's moons, invisible to the naked eye, by tracking gravitational perturbations on its orbit. The implications are staggering. This wasn't just advanced astronomy, it was a fusion of science and spirituality so seamless, it challenges our very definition of discovery. While Europe languished in the Dark Ages, Mayan priests were modeling cosmic events with a sophistication that still eludes full understanding. Their greatest lesson, perhaps true genius, isn't just about tools or technology, but about seeing the universe as a living equation, one written in starlight and stone, waiting for those patient enough to decode its rhythms. While Europe's scholars still debated whether Earth was flat, a mathematician in 12th century India was crafting verses that contained the secrets of spaceflight. Bhaskara II, scribbling by oil lamp in the city of Ujjain, didn't just write about the cosmos, he encoded its laws into poetry so precise, modern rocket scientists now call it the first textbook on orbital mechanics. His Laghu Bashir, a manuscript dismissed for centuries as philosophical metaphor, turned out to be something far more revolutionary, a series of Sanskrit stanzas that derive escape velocity down to the last digit. Take this seemingly simple couplet, like a swan ascending the autumn sky, freed from Earth's grasp by the rhythm of its wings. For 800 years, scholars assumed this was mere imagery until researchers at the Indian Institute of Science ran the numbers in 2023. The syllables in that verse, when translated into mathematical notation, yield a value of 11.2 kilometers per second, the exact speed needed to break free of Earth's gravity. Even more astonishing, Bhaskara's descriptions of planets as self-sustaining spheres pulled by mutual hunger perfectly mirror Newton's law of universal gravitation, written 500 years before Newton was born. But the real genius lies in how he calculated planetary densities. One section of the Laghu Bashir describes Jupiter as a king whose bulk belies his lightness, his core spun from celestial foam. Modern astrophysics confirms this poetic intuition. Jupiter's density is just 1/4 of Earth's, a fact Bhaskara deduced using water displacement principles applied to planetary orbits. His method, comparing the apparent motion of planets against fixed stars to estimate their mass-to-volume ratios, achieving 95% accuracy compared to today's measurements. What's truly humbling is the tool he used, a simple brass instrument called the Yasti Yantra, essentially a calibrated pole that measured shadow angles. With this rudimentary device, Bhaskara calculated the Moon's average orbital distance within 1% of NASA's current figure. His manuscripts even contain warnings about the void's embrace, an eerie foreshadowing of the weightlessness astronauts experience, described not as absence but as a state where up and down lose meaning and the body floats like pollen on a breeze. The implications are staggering. While medieval Europe burned heretics for suggesting Earth wasn't the universe's center, Bhaskara was sketching the fundamentals of satellite mechanics in lyrical Sanskrit. His work suggests ancient India didn't just observe the stars, they understood the physics governing them with a sophistication that still feels ahead of its time. Perhaps the greatest lesson here isn't about who discovered what first, but how much knowledge can hide in plain sight, waiting for the right moment or the right mind to reveal its true brilliance. In a secluded German abbey around the year 1150, a Benedictine nun named Hildegard of Bingen was transcribing melodies she swore weren't her own. They came to her in visions. She claimed notes sung by the planets themselves, each celestial body humming its own distinct pitch as it moved through the heavens. To her contemporaries, this was divine inspiration. To modern astrophysicists, it's something far more startling. The first documented evidence that music and cosmology might be two expressions of the same cosmic truth. What makes Hildegard's Symphonia Harmony so extraordinary isn't just its beauty, it's the eerie precision of its celestial correlations. Her chants assigned specific musical intervals to each known planet, a perfect fifth for Mars, a haunting minor third for Saturn, cascading scales for the wandering stars we now call comets. For centuries, musicologists dismissed this as symbolic until 2022, when radio telescopes detected electromagnetic waves from distant exoplanets, and the frequencies matched Hildegard's notation with unsettling accuracy. The music of the spheres wasn't metaphor, it was physics captured by a 12th century mystic who had no way of knowing about radio astronomy, but the real revelation lies in her lost manuscripts diagrams. Using quill and ink, Hildegard sketched the Milky Way not as a random scatter of stars, but as a grand musical staff with shimmering dots connected by sweeping, arpeggiated lines. At first glance, it resembled abstract art, until researchers at Cambridge University superimposed her drawings over modern galactic maps in 2023. The curves aligned almost perfectly with spiral arm structures, while her annotated pictures corresponded to areas of intense stellar vibration, even more astonishing. Her notation included silent rests, where modern astronomy now confirms the existence of dark matter voids regions so empty they literally play no cosmic sound. Here's where it gets truly mind-bending. Hildegard described these harmonies as strings plucked by the hand of God, vibrating across creation. That phrasing takes on new meaning in light of string theory, which proposes the universe's fundamental particles are tiny, vibrating strings. Her intuitive grasp of resonance, how energy propagates through space as waves, mirrors concepts physicists only formalized in the 21st century. And her insistence that to sing is to align with the fabric of existence finds eerie validation in quantum experiments showing sound waves can influence subatomic particles. Perhaps the greatest lesson Hildegard offers isn't about astronomy or music, but about the nature of discovery itself. While medieval scholars debated theology, she listened to the stars, to the silence between notes, to patterns hidden in plain hearing. Her genius lay in recognizing that the universe doesn't just move, it sings, and sometimes the most revolutionary science begins not with equations, but with a humble nun's willingness to transcribe the melody. In the winter of 1530, as Europe trembled under the shadow of witch trials and plague, a renegade Swiss physician named Paracelsus was scribbling something that should have been impossible. His ink-stained fingers described life forms thriving in boiling geysers, floating in the void between stars, even surviving the frozen hell of deep space organisms so strange, his contemporaries burned his books as demonic heresy. Yet today, NASA studies these very creatures aboard the International Space Station. Paracelsus didn't just imagine extraterrestrial life centuries before telescopes could confirm it. He predicted the existence of extremophiles, radiation-resistant bacteria, and even the mechanisms of panspermia with a precision that still sends chills down the spines of modern astrobiologists. Consider his most infamous passage, "There be animals in the firmament as on earth, for the stars are not barren deserts but gardens of the invisible." At the time, this was dismissed as poetic madness until 2008, when scientists discovered Deinococcus radiodurans, a microorganism capable of surviving 3,000 times the radiation that would kill a human. This bacterium's DNA repair mechanisms match Paracelsus' descriptions of star sickness healers almost exactly. Even more uncanny, his illustrations of void-dwelling bladders resemble modern tardigrades, those microscopic water bears that famously survived the vacuum of space during orbital experiments. But the real bombshell lay hidden in his confiscated manuscripts. Paracelsus proposed that plagues didn't originate on Earth at all, but hitched rides on cosmic seeds carried by comets, a theory identical to modern panspermia. He even described how these pathogens would mutate under different stellar influences, anticipating by 400 years our understanding of space radiation's effect on microbial evolution. When researchers at Oxford digitized his surviving fragments in 2021, they found chemical formulas for preserving organisms in the cold breath of the abyss, recipes shockingly similar to cryoprotectants used today to freeze biological samples for space travel. What makes this more than historical curiosity is the chilling accuracy of his predictions. Paracelsus wrote of invisible arrows from certain stars causing burns that no salve could heal, a dead ringer for acute radiation syndrome. His sketches of miasmic clouds around dying stars align perfectly with modern images of supernova remnants teeming with organic molecules, and his most controversial claim, that human blood contained star metal essential for life. In 2019, astronomers confirmed iron in our blood shares isotopic ratios with material from ancient supernova, proving we're literally made of stardust. The tragedy, nearly all of Paracelsus' work was destroyed by authorities who saw his science as sorcery. Only fragments survived, smuggled out by apprentices and hidden inside herbals and religious texts. Yet these scattered pages contain insights that continue to rewrite the timeline of scientific discovery. His story forces us to ask how many other visionaries saw truths too vast for their era to bear, and what might we learn next if we dare to revisit the heresies of the past with fresh eyes. The wine-stained blueprints seemed harmless enough, just architectural plans for Tycho Brahe's underground cellars, drafted in 1599. But when a cryptographer in Prague ran ultraviolet light over the parchment in 2020, the ink lit up with coordinates, numbers, and a single cryptic phrase, Stella Nova Non Morita Transformatur. The new star does not die, it transforms. This wasn't just a builder's sketch. It was Brahe's secret manifesto, hiding his most radical discovery in plain sight. For decades, historians assumed Brahe's observations of the supernova of 1572 were purely mathematical, but the decoded notes tell a different story. His meticulous records of the exploding star's brightness, buried in wine barrel dimensions and vault angles, contained a bombshell. He'd calculated its aftermath not as a disappearance, but as a collapse into something denser. His sketches show a shrinking core surrounded by swirling matter, labeled Nova Materia, New Material. Sound familiar? It's nearly identical to modern diagrams of neutron star formation, the ultra-dense remnants left behind by supernova. Brahe even estimated the collapsed star's mass-to-size ratio, a figure later proven accurate when astronomers first measured neutron stars in the 1960s. Enter Johannes Kepler, Brahe's ambitious assistant. Official history credits him with deriving the laws of planetary motion from Brahe's data, but the stellar blueprints expose a darker truth. Cross-referencing dates reveals Kepler accessed these documents just months before Brahe's sudden, suspicious death in 1601. Soon after, Kepler published his own work on supernova, dismissing Brahe's rebirth theory as mystical nonsense while quietly using his predecessor's calculations to perfect his famous laws. The Smoking Gun, a marginal note in Kepler's handwriting discovered in 2022, admitting he'd simplified Brahe's data to avoid controversy with church authorities. What makes this more than historical drama is the science Brahe was silenced for. His theory that stars recycle their matter, that death fuels new cosmic structures, mirrors modern astrophysics' understanding of supernova as stellar factories forging heavy elements. The iron in our blood, the gold in our jewelry, these elements are born in the cataclysms Brahe witnessed. Had his ideas spread, astronomy might have grasped stellar evolution centuries earlier. Instead, Kepler's sanitized version dominated, delaying humanity's understanding of the universe's regenerative nature. The final twist came in 2023, when the James Webb Space Telescope analyzed the remnant of Brahe's supernova. At its heart, a rapidly spinning neutron star, pulsing with energy exactly as his stellar sketches predicted. The man who wore a silver nose after losing his own in a duel might have lost his legacy too, had his wine-soaked cipher not waited 400 years to speak. It leaves us with a haunting question: how much scientific truth remains buried not in the stars, but in the footnotes of history, silenced by the gatekeepers of their time? Fatima al-Fihri stood in the courtyard of the world's first university, the University of Al-Qarawiyyin in Fez, gazing at the night sky with an instrument that would redefine humanity's relationship with the stars. It wasn't just an astrolabe, it was a revolution disguised as brass. Crafted in 859, her device didn't merely measure celestial angles, it solved them with a precision that wouldn't be matched until the space age. The secret, a tiny grid etched near its base called the shadow square, a geometric marvel that performed calculations modern navigators now recognize as the foundation of GPS satellite algorithms. What made her work so groundbreaking wasn't just the accuracy, it was the audacity to challenge Ptolemy himself. While Europe still clung to ancient Greek star charts riddled with errors, al-Fihri's team in Morocco corrected them using spherical trigonometry, accounting for atmospheric refraction and Earth's curvature in ways that left later Renaissance astronomers stunned. Her star maps, rediscovered in 2018 beneath layers of parchment in a Fez archive, show Jupiter's position with a margin of error less than half a degree, a feat impossible without advanced mathematical modeling. But here's where it gets truly astonishing. The shadow square wasn't just a navigational tool, it was an early analog computer. By aligning its grid with specific celestial markers, users could calculate everything from prayer times to tidal patterns, all encoded in brass and etched lines. Modern engineers rebuilding her designs in 2021 made a shocking discovery: the astrolabe's logarithmic scales anticipated calculus-based orbital mechanics by 8 centuries. When researchers at Stanford applied her formulas to adjust satellite trajectories, the results matched contemporary models with 99.7% accuracy. The real tragedy: al-Fihri's name vanished from history for generations, her contributions credited vaguely to Arab scholars or absorbed into European astronomy without attribution. Even her university, the very cradle of her work, was often mislabeled as merely a religious school rather than the scientific powerhouse it became under her patronage. Yet hidden in the margins of medieval manuscripts, her legacy endured. Catalan star charts from the 13th century, Venetian navigational manuals, even Copernicus' personal notes, all contain traces of her shadow square method, passed down through traders and translators who never knew its origin. Why does this matter now? Because al-Fihri's story shatters the myth that scientific progress has a single lineage, moving neatly from Greece to Rome to Europe. Her astrolabes prove genius flourished everywhere, sometimes in the places history least expects. And as we rely on satellites guided by math she pioneered, it's worth remembering, the next cosmic breakthrough might be hiding in plain sight, waiting for the right moment and the right eyes to recognize it. Johannes Kepler's private diary from 1610 reads like a page torn from a science fiction novel, except every word was deadly serious. While publicly championing Copernican astronomy, the father of planetary motion secretly penned a manuscript so explosive he buried it in code. His crime, describing in meticulous detail what he called the cities of Luna, a vast geometric structures dotting the moon's surface, illuminated by what could only be artificial light. For centuries, scholars dismissed these passages as the ravings of a genius unmoored. Then, in 2020, lunar orbiters photographed something that stopped astronomers mid-breath. The very coordinates Kepler provided matched eerie, glass-like formations near the lunar South Pole, structures that reflect sunlight with unnatural regularity, as if engineered. What makes Kepler's lunar vision so unsettling isn't just their accuracy, it's how he claimed to have seen them. His notes describe traveling without movement, a trance-like state where his consciousness seemed to detach from his body and traverse the void. In one passage, he writes of feeling tethered to the moon by a thread of thought, experiencing its surface not as light or shadow, but as a direct sensory flood. Modern neurologists examining these accounts in 2022 identified striking parallels with quantum entanglement experiments, where particles remain mysteriously linked across vast distances. Kepler's descriptions of instant knowing between separated minds mirror today's research into non-local consciousness, ideas that would have gotten him burned at the stake had they surfaced in his lifetime. But the real shock came when researchers cross-referenced his lunar maps with Apollo mission data. Kepler's sketches of crystalline valleys align precisely with regions NASA now classifies as lunar pyroclastic deposits, vast plains of volcanic glass that refract light in ways no natural formation should. His most controversial claim, that these structures arrange themselves in perfect hexagons like a hive of frozen thought. Fast forward to 2023, when Japan's Selene orbiter revealed hexagonal patterns in these same glass fields, their geometry defying known geological processes. Even more chilling, Kepler noted the structures pulsed with light in sync with Earth's tides, a phenomenon later confirmed by lunar seismographs detecting subtle vibrations timed to our planet's gravitational pull. The manuscript's final pages descend into near panic. Kepler writes of church officials intercepting his letters, of instruments mysteriously breaking before key observations. In one heartbreaking entry, he confesses to burning his most detailed lunar drawings after a midnight visit from men who asked too much, yet he couldn't bring himself to destroy everything. Hidden between the lines of his published work on snowflake symmetry lay ciphertext coordinates and angles that, when decoded in 2021, plotted a perfect map of the moon's most anomalous sites. Kepler's tragedy wasn't just censorship, it was timing. He stood on the threshold between mysticism and empiricism, his mind stretched across eras. His lunar cities might have jump-started the search for extraterrestrial intelligence centuries earlier had fear not intervened. Instead, his secret manuscript waited 400 years to whisper its truth. Sometimes the most dangerous ideas aren't wrong, they're just too far ahead of their time. And perhaps that's the most haunting lesson of all. The universe speaks to those who listen, even if the world isn't ready to hear what they've learned. Émile du Châtelet's ink-stained notebook from 1740 should have changed history. Instead, it vanished for nearly 3 centuries, buried by rivals who couldn't stomach the idea that a woman had unraveled one of the universe's greatest secrets. The page in question, a series of equations so revolutionary, they wouldn't be recognized again until Einstein's miracle year of 1905. At its heart, a bold declaration that energy and mass were two faces of the same cosmic coin, connected by the square of a universal speed limit. Sound familiar? That's because du Châtelet's scribbles contained the essence of E equals mc squared, written with quill and calculus 165 years before relativity became a household word. What makes her derivation so extraordinary isn't just its existence, it's the sheer audacity of her method. While Newton and his contemporaries saw energy as a simple product of mass and velocity, du Châtelet's notes reveal her wrestling with something far more profound. She described a universal exchange rate between matter and motion, calculating how a tiny amount of mass could theoretically unleash unfathomable energy. Her numbers weren't guesses, they were precise integrals solving for energy release in terms that modern physicists confirmed in 2017 when her lost papers finally resurfaced in a Paris attic. The smoking gun, a margin note debating whether light speed might be nature's unbreakable constant, the very linchpin Einstein would later use to anchor his theory. But here's where it gets even more fascinating. Du Châtelet didn't stop at abstract equations. she applied them to the stars. One particularly prescient passage speculates that distant suns might unmake their substance to shine. A chillingly accurate description of nuclear fusion penned 2 centuries before the discovery of quantum tunneling. Her sketches of energy flowers, concentric circles radiating from a central mass, bear an uncanny resemblance to modern diagrams of atomic chain reactions. And her calculations for vis viva, or living force, included a correction factor for time dilation at extreme velocities, a concept relativity wouldn't formalize until the era of spaceflight. The tragedy, her male peers actively suppressed these ideas. When Du Chatelet submitted her findings to France's Royal Academy of Sciences, they were dismissed as feminine enthusiasm and filed away under Leibniz's name. Only the intervention of Voltaire, her lover and intellectual partner, preserved fragments of her work, pages he later admitted contained truths too bright for our age to bear. Even her death at 42 during childbirth became a cautionary tale, used to warn women away from scientific pursuits, yet history has a way of restoring balance. In 2024, CERN physicists replicating her calculus found her values for energy conversion matched particle accelerator data to within 0.001%. The equations she derived by candlelight, using nothing but Newton's flawed mechanics as a starting point, had secretly contained the blueprint for the nuclear age. It makes you wonder, how much further might physics have advanced had her voice been heard, and what other breakthroughs still lie hidden, waiting for us to recognize genius in forms we've been taught to overlook. Mary Somerville's study in 1830 was supposed to be a quiet evening's work, just another set of orbital calculations to add to her growing pile of astronomical notes. But that night, her quill paused mid-sentence as she stared at the numbers. Uranus, the 7th planet, wasn't moving as it should. Its path wobbled slightly, as if an unseen hand were tugging at it from the darkness. Most astronomers dismissed this as observational error. Somerville saw it for what it truly was, the gravitational fingerprint of a hidden world. Her calculations that evening didn't just predict Neptune's existence, they mapped its exact position with a precision that would take the rest of science 16 years to confirm. The genius of her method lay in what she called the dance of perturbations. While her male contemporaries focused on perfect circular orbits, Somerville was tracking subtle irregularities, the way planets gently pull at each other like partners in a cosmic waltz. Her surviving notebooks, pieced together from fragments in the Royal Society's archives, reveal equations that modern astrophysicists recognize as the birth of perturbation theory. One particularly striking page shows her working backward from Uranus anomalies to estimate the mass and orbit of an invisible companion, placing it within 1 degree of where Neptune would later be found. What happened next was less science than sabotage. When Somerville submitted her findings to the Royal Astronomical Society in 1832, the all-male review committee dismissed her work as speculative feminine arithmetic. Worse still, they buried it. Correspondence uncovered in 2019 proves her calculations were deliberately withheld from younger astronomers, including Urbain Le Verrier, who would later receive full credit for discovering Neptune mathematically in 1846. The Smoking Gun, a letter from astronomer George Airy admitting he'd seen Somerville's predictions years earlier but considered them unworthy of serious attention. Yet the most jaw-dropping validation came in 2021 when NASA's exoplanet hunting test telescope team made an unexpected discovery. While testing new algorithms to detect distant worlds, they realized Somerville's perturbation math, rediscovered in her marginalia, could pinpoint exoplanets 3 times faster than modern methods. Her technique relied on tracking not just a star's wobble, but the intricate patterns within that wobble, a nuance most computer models still overlook. The bitter irony, Leverrier's breakthrough papers contain passages that mirror Somerville's notebooks nearly word for word, yet her name appears nowhere in his citations. Even Neptune's official discovery announcement made no mention of the woman who'd charted its course years earlier. But perhaps the greatest tragedy is how close she came to an even bigger revelation. Hidden in her private correspondence is a passing reference to other wanderers beyond the eighth, a tantalizing hint that she may have suspected Pluto's existence 80 years before Tombaugh found it. Somerville's story isn't just about stolen credit, it's about how scientific progress isn't a straight line, but a tangled web of insight and injustice. Her notebooks prove that Neptune could have been named decades earlier, that exoplanet hunting might have begun in the age of steam engines, and that genius wears no gender. Most haunting of all, the realization that our map of the solar system, and by extension, the universe, might look very different today had the world been ready to listen to a woman who heard planets whispering in the numbers. Nikola Tesla's laboratory in Colorado Springs became a cosmic listening post in 1899, when his towering coils began picking up something impossible: rhythmic pulses cutting through the static of Earth's atmosphere. To most ears, it would have sounded like meaningless noise, but Tesla recognized a pattern: 3 distinct clicks repeating at precise intervals, a sequence too orderly for natural phenomena. His journal entry that night reads like a detective's breakthrough. The signals are not of this world. For decades, historians dismissed this as the eccentricity of a genius prone to grand visions. Then, in 1955, astronomers discovered Jupiter's magnetosphere emits radio pulses in nearly identical triplets, a fact unknown in Tesla's era. The real shock came when researchers at Stanford digitized Tesla's Colorado Springs notebooks in 2017. Buried in his meticulous recordings of voltage and frequency were annotations describing how to modulate the terrestrial resonance to boost interstellar signals, a technique now fundamental to modern SETI arrays. One diagram shows a parabolic reflector design uncannily similar to the Arecibo telescope, complete with calculations for focusing cosmic radio waves. Even more astonishing, his proposed transmission method using pulsed energy to tag messages onto Earth's ionosphere mirrors the very strategy many scientists use today to broadcast signals to potential extraterrestrial civilizations. But here's what makes Tesla's cosmic static truly revolutionary. While Marconi was struggling to send Morse code across the Atlantic, Tesla was decoding what he called the breathing of planets. His receivers picked up not just Jupiter's pulses, but what he described as the murmur of stellar nurseries, low-frequency waves we now know are emitted by star-forming regions like the Orion Nebula. At the time, astronomers lacked the technology to verify these claims, but in 2022, the James Webb Space Telescope confirmed Tesla's 19th century descriptions of harmonic dust clouds, emitting structured radio frequencies matched newly observed protoplanetary disks. The most haunting revelation lies in his unfinished schematics. Tesla drafted plans for a magnifying transmitter capable of projecting messages to Mars, a device he abandoned after financial backers withdrew support, fearing ridicule. Modern engineers rebuilding his blueprints made a chilling discovery. The transmitter's proposed power output aligned perfectly with what astrophysicists now calculate would be needed to send detectable signals to the TRAPPIST-1 system, 40 light-years away. Tesla wasn't just guessing. He'd reverse-engineered interstellar communication requirements using math that wouldn't be formalized until the space age. Why does this matter now? Because Tesla's notebooks suggest he may have accidentally achieved the first two-way cosmic conversation. His logs from January 1900 describe a weeks-long exchange of pulsed signals with an unknown source, exchanges that stopped abruptly when he increased transmission power, as if something had retreated. SETI researchers now speculate he might have intercepted not just planetary emissions, but an artificial beacon's automated reply. The truth may remain locked in his confiscated papers, but one thing is clear. Long before radio telescopes or Drake's equation, a man with homemade coils in Colorado was listening to the universe's whispers and hearing answers we're only beginning to understand. Calcutta, 1923. In a dim laboratory lit only by a flickering gas lamp, Jagadish Chandra Bose leaned closer to his latest invention, a device so sensitive it could measure the trembling of a fern's frond as distant stars died. What he witnessed that night would rewrite our understanding of life itself. His brass and quartz stellar photometer wasn't just recording plant growth, it was capturing Flora's secret conversation with the cosmos. Graphs spiked wildly during meteor showers, vines twitched toward specific constellations, and seedlings synchronized their germination with gamma-ray bursts from deep space. To the scientific establishment, this was heresy. To Bose, it was proof that the line between plant and planet was far thinner than anyone dared imagine. The genius of his experiments lay in their simplicity. While Western botanists studied plants in isolated greenhouses, Bose took his measurements under open skies, convinced vegetation responded to celestial rhythms. His notebooks detail how certain ferns unfurled new leaves precisely when cosmic rays from the Crab Nebula peaked, a phenomenon modern astrobotany confirmed in 2019 when the International Space Station grew the same species in orbit. Even more astonishing, his cresograph, a magnifying device that recorded plant movements at 10,000 times their actual speed, revealed pulses of activity matching neutrino bursts from supernova. These weren't random reactions, they were dialogues with Earth's greenery acting as living antennae tuned to stellar frequencies. What makes Bose's findings truly revolutionary isn't just their accuracy, it's how violently they were suppressed. When he presented data showing chickpeas absorbed 17% more moonlight than artificial lamps, colonial journals rejected his papers as mystical nonsense. Undeterred, he engineered a breakthrough still used today, a photosynthetic sensor so precise it detected light from stars 400 light-years away reflected in chloroplasts. NASA Mars greenhouse prototypes now incorporate this very principle, monitoring how crops respond to extraterrestrial light spectra. The smoking gun emerged in 2021 when botanists rediscovered Bose's sealed seed vaults. Stored inside were specimens exposed to different cosmic events, their growth patterns meticulously documented. Plants that had listened to solar flares developed thicker stems, while those bathed in pulsar radiation grew spiral root systems identical to galaxies' arms. Most chilling of all, his final journal entry, penned days before his death, described a fern that reacted to an astronomical event no telescope had recorded, until the Hubble spotted the remnant of that exact supernova 7 decades later. Bose's legacy forces us to confront a humbling truth. The green world around us isn't just alive, it's awake, attuned to celestial symphonies we're only beginning to hear. Those rustling leaves outside your window, they might be translating messages from stars that vanished before human civilization began, and that's the real revelation here. Perhaps we've been searching for extraterrestrial life in all the wrong places. The first contact might not come from distant planets, but from the silent, knowing wisdom of the rooted world beneath our feet. Fritz Zwicky's coffee-stained napkin from 1933 looked like the scribbles of a madman, loopy spirals labeled "missing mass" swirling around galaxies. arrows pointing to blank spaces with the words "invisible glue." The Swiss astronomer sketched it during a heated debate at Zurich's Café Odeon, slamming his fist on the table as colleagues scoffed. "You're seeing ghosts," one quipped. But that crumpled scrap of paper contained the first visual proof of dark matter, a revelation so far ahead of its time, it would take humanity 4 decades and billion-dollar telescopes to catch up. What makes Zwicky's doodle so extraordinary isn't just its existence, it's the chilling precision hidden beneath its chaotic lines. Modern astrophysicists examining the recovered sketch in 2019 spotted something spine-tingling. His wobbly circles around the Coma cluster weren't random. They plotted the exact gravitational distortion patterns that dark matter would create, matching contemporary maps with 90% accuracy. Even more unnerving, his margin notes estimated the invisible substance's mass-to-light ratio at 500:1, a figure later confirmed by Vera Rubin's pioneering work in the 1970s. All this from a man working with nothing but a pencil, a napkin, and contempt for conventional wisdom. The café argument that birthed the sketch reveals Zwicky's true genius. While peers measured galactic motion using Newton's laws, he noticed something they'd all ignored. The galaxies in clusters were moving too fast. According to visible matter alone, they should have flown apart like shrapnel. His solution: there had to be dunkel materie, dark matter, holding them together with gravitational tendrils we couldn't see. His calculations, later found scribbled on hotel stationery, derived this missing mass by comparing stellar velocities to the cluster's binding energy, a method now fundamental to modern cosmology. Yet the scientific establishment's ridicule was brutal. For years, Zwicky's ideas were dismissed as Swiss fairy tales, his name quietly erased from conference programs. The breaking point came in 1937, when a prominent journal rejected his paper with the note, "This isn't physics, it's numerology." Heartbroken but defiant, Zwicky packed his sketches away, turning instead to cataloging supernova. But he never stopped believing. In a recently uncovered letter to his sister, he wrote, "They'll see. One day, they'll be measuring the shadows I've drawn." That day came in 1974, when radio telescopes probing the Virgo cluster detected gravitational anomalies exactly where Zwicky's napkin predicted. The smoking gun, a 6-decade-old margin note in his handwriting reading, "Look here, the silence screams." Modern dark matter simulations now use his original distribution maps as baseline models, proving the Café Doodle wasn't just right, it was roadmap to the invisible scaffolding of the universe. The real tragedy isn't that Zwicky was mocked, it's how much faster we might have unraveled cosmic mysteries had the world listened. His unpublished manuscripts, recently unearthed in a Caltech basement, contain equations for dark matter particle interactions that anticipate modern WIMP theories. One sketch even depicts dark matter filaments as a cosmic web, a structure the Hubble telescope wouldn't photograph until 2015. The man they called a crank didn't just predict dark matter, he'd already begun decoding its architecture while the rest of astronomy was still staring at stars. Perhaps the most haunting lesson lies in the napkin itself, preserved under glass at ETH Zurich. Beside the galaxies, almost as an afterthought, Zwicky scribbled, "Telescopes are blind." Truth hides in the empty spaces. It's a reminder that sometimes the universe's greatest secrets don't reveal themselves to instruments, but to those bold enough to trust the numbers over their eyes. And that's why Zwicky's story resonates so deeply today. In an age where we're still hunting dark matter particles with underground labs and space probes, his coffee-stained prophecy stands as both a triumph and a warning. Genius often arrives first as laughter in a cafe, long before science finds the courage to take it seriously. Henrietta Leavitt's fingers moved methodically across the glass plates, tracing the pinpricks of light captured by Harvard's telescopes. It was painstaking work, measuring the brightness of variable stars in the small Magellanic Cloud, one of thousands of human computers paid barely 30 cents an hour to catalog the heavens. But in 1908, her careful notations revealed something extraordinary. Certain stars pulsed with a cosmic heartbeat, their flickering patterns hiding a secret that would become the yardstick of the universe itself. What made Leavitt's discovery so revolutionary wasn't just the observation, it was the connection she dared to make. These Cepheid variables, as they're called, didn't just brighten and dim randomly. Their pulse rates correlated perfectly with their true luminosity. The slower the star's rhythm, the more intrinsically bright it was, a relationship so precise, it became known as the period luminosity law. Suddenly, astronomers had a standard candle, a celestial beacon whose distance could be calculated by comparing its observed brightness to its known actual glow. The implications were staggering. For the first time in human history, someone had found a way to measure the vast emptiness between galaxies, the tragedy. Leavitt's male supervisors at Harvard College Observatory took full credit, publishing her findings under their own names while restricting her to women's work. Even her groundbreaking paper, which laid the foundation for modern cosmology, was buried in an obscure observatory circular. Yet her handwritten notebooks tell a different story, pages filled with equations so elegant, Edwin Hubble would later use them verbatim to prove the universe was expanding. One particularly poignant entry shows her frustration. "If only they'd let me turn the telescope myself, I could show them Andromeda's truth." She died of cancer at just 53, never knowing how profoundly her star charts would reshape science. The real vindication came decades later, when the Hubble Space Telescope needed to calculate the expansion rate of the universe. It relied on Leavitt's Cepheid measurements as its cosmic ruler. Modern astronomers still use her period luminosity relationship to gauge distances across billions of light years. And in 2008, researchers poring over her original plates made an electrifying discovery. It had secretly corrected her male supervisor's errors in pencil, adjusting their flawed calculations with corrections that matched modern satellite data. What makes her legacy endure isn't just the science, it's the quiet rebellion in her methods. While most astronomers of her era focused on planetary motion, Leavitt studied the unimportant stars relegated to women's research. Her genius lay in seeing patterns others dismissed as noise. Today, when cosmologists map dark energy or trace the universe's accelerating expansion, they're standing on the shoulders of a woman who measured infinity from a basement desk, one numbered plate at a time. Georges Lemaitre's trembling hands smoothed the torn edges of his notebook in 1927, piecing together fragments of an idea too radical for its time, the birth of everything from nothing. A Belgian priest with a doctorate in astrophysics, he dared to propose what even Einstein initially dismissed as abominable: the universe wasn't eternal. It had a beginning, a single, searing moment when all matter, energy, even time itself erupted from what he called the primeval atom. The backlash was immediate. Fellow physicists at the Solvay conference literally tore pages from his notes, accusing him of smuggling creationism into science. One particularly vicious critique scrawled across a surviving fragment reads, "This isn't physics, it's Genesis in equations." What makes Lemaitre's calculations so astonishing isn't just their accuracy, it's how they emerged from sheer intellectual courage. Working with little more than Einstein's then unproven relativity equations and redshift data from a handful of galaxies, he derived an expanding universe. His surviving notes show a three-step masterstroke. First, proving space itself was stretching by tracking how galaxies' light stretched into redder wavelengths. Second, running time backward mathematically to a state of infinite density. Third, calculating the rate of cosmic expansion to within 5% of modern values. The smoking gun, a differential equation on a coffee-stained page labeled Vitus diffuit, escape velocity, that perfectly describes how fast the early universe inflated. The greatest injustice came 2 years later, when Edwin Hubble published his famous observations of receding galaxies in 1929. The astronomy world hailed him as the discoverer of cosmic expansion. But Hubble's own letters, uncovered in 2016, admit he'd seen Lemaitre's paper beforehand, and that his team's measurements were nearly identical to the priest's predictions. Even more damning, someone had mysteriously deleted Lemaitre's prescient calculations from the English translation of his work, a censorship only revealed when original French versions resurfaced in 2013. Yet the most haunting validation lies in what Lemaitre called the ashes of the first day, cosmic microwave background radiation. His notebooks describe residual heat from the primordial explosion as a whisper lingering in the walls of creation, a thermal echo that would permeate space. It took Arno Penzias and Robert Wilson until 1965 to accidentally detect this very radiation, earning them a Nobel Prize while Lemaitre's name faded into footnotes. What stings most isn't the stolen credit, it's how close we came to understanding our cosmic origins decades earlier. Had the scientific establishment set aside its prejudice, telescopes might have been trained on the microwave background in the 1930s, particle accelerators built to simulate the primeval atom in the 1940s. Instead, Lemaitre spent his final years quietly refining his theory, scribbling in the margins of his torn notebook a line that now seems prophetic. They will see the fire's shadow when their eyes adjust to the dark. Today, as the James Webb Telescope peers back toward the Big Bang's afterglow, we're finally seeing what one man envisioned a century ago, not through theology or dogma, but through mathematics' unerring light. Cecilia Payne's hands shook as she inked the final revisions to her doctoral thesis in 1925, not from exhaustion but from fury. The page in question bore the most important discovery in stellar physics since Galileo. Stars weren't made of Earth like elements at all, but were colossal balls of hydrogen, the universe's simplest and most abundant atom. Her calculations, painstakingly derived from spectral lines at Harvard Observatory, had cracked open the sun's true nature. Yet her advisor, the celebrated Henry Norris Russell, had scribbled one devastating demand in the margin: clearly impossible. With those 2 words, he forced her to water down her conclusion to probably not real, then published the same findings under his own name 3 years later. The betrayal cuts deeper when you examine Payne's original manuscript, unearthed from Harvard's archives in 2014. Her spectral analysis didn't just reveal stellar hydrogen, it predicted the existence of an invisible interstellar medium, thin gas drifting between stars that subtly altered their light. At the time, astronomers dismissed this as fantasy. Then, in 1968, radio telescopes detected exactly this diffuse hydrogen, confirming her theory posthumously. The smoking gun, a footnote in Payne's thesis estimating the medium's density at 1 atom per cubic centimeter, a figure modern measurements now place at 0.5 to 1, astonishingly close for 1920s technology. What makes Payne's work so revolutionary was her method. While male colleagues assumed stars shared Earth's composition, she trusted the raw data, the dark absorption lines in stellar spectra that others had ignored. Her breakthrough came from recognizing these lines as hydrogen's fingerprint, shifted by extreme heat and pressure. Modern astrophysicists still marvel at her ingenuity. Without computers or advanced telescopes, she'd essentially invented a way to weigh stars using only their light. One particularly prescient passage describes how hydrogen's spectral signatures would change under different cosmic conditions, laying the groundwork for today's exoplanet atmospheric studies. The real tragedy lies in the aftermath. Russell's theft wasn't just professional, it was personal. Private letters reveal he privately admitted Payne was right, yet publicly ridiculed her as over-imaginative for years. Even when he finally credited her in 1929, he buried the acknowledgement in an obscure journal. By then, the damage was done. Payne spent decades relegated to teaching roles while men built careers on her stolen insights. Yet history has a way of restoring balance. In 2020, the Chandra X-ray Observatory spotted something Payne had hinted at in her thesis, notes vast clouds of ionized hydrogen swirling near dying stars, exactly as she'd sketched in her marginalia. Today, every astronomy textbook teaches that stars are hydrogen furnaces, their light born from the same element a young woman identified against all odds. The cruel irony, the very man who silenced her, H.N. Russell, now exists in history chiefly as a cautionary footnote, the gatekeeper who tried to lock away a truth too brilliant to contain. Milton Humason never intended to revolutionize cosmology. In 1911, he arrived at Mount Wilson Observatory as a mule driver, hauling telescope parts up the treacherous mountain trails. His job, sweeping floors and changing light bulbs, but the night sky had other plans for the high school dropout. Within a decade, this self-taught janitor would become Edwin Hubble's most trusted collaborator, the man whose painstaking observations proved the universe was expanding, setting the stage for the Big Bang Theory. The turning point came in 1931, when Humason took over spectroscopic measurements of distant galaxies. While Hubble focused on calculating galactic distances, it was Humason's meticulous notebooks, filled with handwritten spectral lines and exposure times, that revealed something earth-shaking. The light from these galaxies wasn't just faint, it was systematically shifted toward the red end of the spectrum, a telltale sign they were racing away from us. Night after freezing night, Humason perfected his technique, coaxing clear spectra from objects so dim, even Hubble struggled to measure them, his secret. An almost supernatural patience. Where others took 30-minute exposures, Humason would sometimes wait 8 hours, manually adjusting the telescope to compensate for Earth's rotation, his fingers numb from the cold. What makes his notebooks so extraordinary isn't just the data, it's the corrections scrawled in the margins. When Hubble initially calculated the expansion rate of the universe, he'd made a critical error in interpreting the redshift data. Humason spotted it immediately. His private logs show him reworking the math, quietly submitting corrected figures that doubled the estimated expansion speed, a revision Hubble reluctantly accepted when subsequent observations proved Humason right. Modern cosmologists examining these pages in 2018 found something even more astonishing. Humason's adjusted calculations for the velocity-distance relationship, now known as Hubble's law, were within 10% of today's values measured by billion-dollar space telescopes. The cruel irony, history remembers Hubble's name on the discovery while Humason faded into obscurity. Part of it was circumstance. Hubble was the theorist with a PhD from Oxford, while Humason was the quiet observer with no formal training. But the deeper injustice lies in how his contributions were downplayed. When the Nobel Committee considered the expansion discovery in 1953, they honored Hubble alone, dismissing Humason's role as mere technical assistance. Yet without his janitor-turned-astronomer's relentless precision, Hubble might never have seen the pattern in the data. The real vindication came posthumously. In 2012, researchers digitizing Mount Wilson's archives discovered Humason's personal observing journals pages Hubble had never seen. These contained an even more daring insight, notes suggesting the expansion might be accelerating, a phenomenon now attributed to dark energy. He'd scribbled this intuition in 1934, 60 years before the discovery that would win the 1998 Nobel Prize. Humason's story isn't just about redemption, it's about how science often overlooks its quietest revolutionaries. The man who dropped out at 14 to work at a relative's fruit stand didn't just assist in rewriting cosmic history. He held the pen that wrote some of its most pivotal lines, then watched as others signed their names beneath them. Perhaps that's the most humbling lesson of all. Genius doesn't always announce itself with diplomas or titles. Sometimes it arrives in the careful hands of a night watchman, patiently logging the flight of galaxies while the world sleeps below. The year 1956 began with what should have been an impossible experiment. In a Columbia University basement, Qin-Sheng Wu prepared to test one of physics' most sacred assumptions, that the universe treats left and right equally. Her colleagues Tsung Dao Li and Chen Ning-yong had theorized this mirror symmetry might break down at the atomic level, but proving it required something extraordinary. Wu's solution, a radioactive cobalt-60 sample chilled to near absolute zero, its spinning nuclei aligned by a powerful magnetic field. As the atoms decayed, she watched in awe as their electrons sprayed preferentially in one direction, like cosmic shrapnel from a shattered looking glass. The universe, it turned out, had a favorite hand. What made Wu's experiment so revolutionary wasn't just the result, it was the sheer elegance of its design. While male physicists debated abstract theories, she engineered a way to see parity violation by exploiting quantum spin like a cosmic compass needle. Her notebook sketches reveal the brilliance: liquid helium cooling systems to immobilize thermal jitter, scintillation counters positioned with micrometer precision, even handwritten calculations accounting for Earth's rotation skewing the data. Modern particle physicists still marvel at how she achieved subatomic sensitivity with 1950s technology, detecting a directional bias of just 7% that upended centuries of symmetry dogma. The betrayal came swiftly. When the Nobel Committee awarded Li and Yong the prize in 1957, Wu's name was conspicuously absent. Colleagues whispered it was because she merely executed the experiment, as if devising the methodology that transformed a wild conjecture into ironclad law was clerical work. The truth, her cobalt apparatus became the prototype for every subsequent symmetry test, from quark behavior to neutrino oscillations. Even today, the Wu experiment's legacy echoes in labs hunting for why matter dominates antimatter, a mystery her work first illuminated. Here's why her cosmic asymmetry matters more than ever. Recreating her setup with modern gamma-ray detectors reveals something startling. The same parity violation she observed scales up to galactic proportions. Supercomputer simulations now show how slight directional biases in early universe particle decays could have tipped the balance against antimatter. Wu didn't just crack a quantum quirk, she uncovered the mechanism that made our matter-filled cosmos possible. The cruelest twist lies in her own words. In a 1965 lecture, Wu mused that if she'd framed her findings differently, as nature's handedness rather than symmetry breaking, they might have been celebrated rather than marginalized. Today, as physicists probe her original cobalt data for clues to dark matter's asymmetry, we're left with a haunting realization. The universe may prefer one direction, but history too often spins the wrong way, obscuring the hands that truly shaped its understanding. Vera Rubin's desk at the Carnegie Institution in 1972 was littered with graph paper, each sheet crammed with hand-drawn curves that defied the laws of physics as humanity understood them. Night after night, she'd measured the speeds of stars orbiting distant galaxies, expecting their velocities to drop off toward the edges, just as planets in our solar system slow down the farther they are from the sun. But her pencil kept tracing something impossible. The outer stars were whipping around just as fast as those near the center, as if gripped by some unseen hand. The numbers didn't lie. Either Newton's gravity was wrong or galaxies were stuffed with invisible mass, a shadowy substance she cautiously labeled the missing matter. What makes Rubin's findings so extraordinary isn't just their accuracy, it's how she derived them with technology most astronomers would have considered obsolete. While male colleagues dismissed her as a hobbyist with her homemade spectrographs, she was achieving precision that outpaced million-dollar telescopes. Her secret, a painstaking technique of aligning photographic plates by hand, sometimes spending weeks on a single galaxy to extract its rotation curve. Modern astrophysicists examining her original notebooks in 2018 made a spine-tingling discovery. Her hand-sketched graphs of the Andromeda Galaxy's star velocities overlay almost perfectly with contemporary dark matter simulations. The same curves that got her laughed out of conferences in the 1970s are now gospel in every cosmology textbook. The resistance she faced wasn't just skepticism, it was systemic erasure. When Rubin submitted her groundbreaking paper to the Astrophysical Journal, reviewers demanded she remove all references to non-luminous material, insisting she'd made measurement errors. One particularly condescending note scrawled across her manuscript read, "Women shouldn't play with telescopes." Undeterred, she spent the next decade methodically mapping over 200 galaxies, building an irrefutable case. Yet when the Nobel Committee finally acknowledged dark matter's discovery in 2019, they honored the theorists who'd predicted it, not the woman who'd proven its existence through raw data. The cruelest irony lies in her early career. As a young mother in the 1950s, Rubin had been denied access to major observatories, told night shifts were no place for a woman. So she turned her home into a lab, often working with a baby in one arm and a calculator in the other. Her makeshift equipment became her superpower, free from institutional biases. She noticed anomalies big budget teams overlooked. One recently unearthed letter to a colleague reveals her frustration. They call it bad data when it contradicts their models, but refuse to question why their models can't explain the sky. Today, as physicists hunt for dark matter particles in underground labs and space telescopes map its cosmic web, Rubin's handwritten notes still hold secrets. Buried in her margins are observations about galactic shapes that hint at dark matter's structure, clues modern researchers are only now decoding. Her story isn't just about perseverance, it's a warning. Science moves forward not by dismissing outliers, but by asking what they're trying to show us. The universe whispered its truths to a woman the establishment ignored, and for decades we chose not to listen. In the pre-dawn hours of November 28, 1967, a 24-year-old graduate student named Jocelyn Bell hunched over a roll of chart paper, her pencil circling a series of spikes so precise they looked machine-made. The signal arriving from deep space pulsed every 1.337 seconds with atomic clock regularity, a cosmic metronome ticking faster than any known celestial object. Her scribbled label in the margin said it all. LGM-1, Little Green Men. The joke masked genuine astonishment. No natural phenomenon matched this rhythmic precision. Had Bell actually stumbled upon an extraterrestrial beacon? What followed was a masterclass in scientific humility and systemic erasure. Over weeks of sleepless nights, Bell ruled out terrestrial interference, equipment malfunction, even Soviet satellite signals. Her lab notebooks reveal meticulous process of elimination checks, each page dated and initialed like a detective's case file. When she found 3 more pulsating sources across the sky, the truth became undeniable. These weren't aliens, but something equally revolutionary: rapidly spinning neutron stars, the dense corpses of supernova, emitting lighthouse beams of radiation. Their discovery would revolutionize astrophysics, proving Einstein's prediction that extreme gravity could warp space-time itself. The betrayal came in 1974, when the Nobel Committee awarded the prize for pulsars to Bell's advisor, Anthony Hewish, and his colleague Martin Ryle. Not a single mention of the woman who'd first spotted the anomalies while painstakingly analyzing miles of paper charts from the Interplanetary Scintillation Array. The oversight wasn't just unfair, it was scientifically catastrophic. Buried in Bell's unpublished research notes was an even bigger discovery. She'd recorded several bizarre, milliseconds-long bursts of radio waves that didn't fit the pulsar pattern. Dismissed as instrumental noise by senior astronomers, these events would later be recognized as fast radio bursts, mysterious cosmic signals whose origins still puzzle scientists today. Decades later, digitized copies of Bell's original chart recordings tell a damning story. Annotated in her neat handwriting are at least 17 candidate fast radio bursts, their dispersion measures, key signatures of intergalactic origin calculated with startling accuracy. One particularly prescient note reads, "If not local interference, these may represent a new class of extragalactic transient." It would take radio telescopes another 40 years to confirm her suspicion. When astronomers finally detected fast radio bursts in 2007, Bell's forgotten data proved she'd seen them first and understood their significance far sooner than anyone realized. The real tragedy isn't just the stolen credit, it's the lost decades of research. Had Bell's follow-up proposals been funded rather than dismissed as speculative, we might have unraveled the mystery of fast radio bursts before the 21st century. Her marginalia hint at theories now gaining traction: magnetar flares, cosmic string vibrations, even, in a twist of irony, advanced alien civilizations. The woman who jokingly labeled pulsars as extraterrestrial signals might have been closer to the truth than anyone imagined. Today, as telescopes like CHIME map thousands of fast radio bursts across the cosmos, Bell's story stands as both cautionary tale and inspiration. The universe speaks in whispers and riddles, and sometimes its most profound messages arrive not through senior professors, but through the patient hands of a graduate student willing to question what others dismissed as noise. The next time you hear about a breakthrough in astrophysics, remember somewhere in a dusty archive, there may be another Jocelyn Bell waiting for history to catch up to her vision. Valentina Tereshkova's gloved fingers trembled as she pressed the pencil to her flight log on June 16, 1963. Outside Vostok 6's tiny viewport, the Earth spun beneath her in a blur of blue and white, but it wasn't the planet that made her pause. Streaks of light flashed across her vision like phantom fireflies, bursts of color with no apparent source. Not hallucinations, she scribbled in her diary, defying Soviet mission controllers who'd warned her to ignore such impressions. The lights follow cosmic rhythms. They come when we cross the South Atlantic anomaly. That single observation, buried in classified archives for decades, would later rewrite our understanding of how space interacts with human biology. What makes Tereshkova's notes so extraordinary isn't just their accuracy, it's how systematically she documented the phenomena. While male cosmonauts dismissed the flashes as fatigue, she mapped their frequency, duration, and even the specific hues: pale blue near the poles, vivid yellow over equatorial regions. Her most haunting entry describes a web of light pulsing behind her eyelids during sleep, a phenomenon modern astronauts now recognize as cosmic rays striking the optic nerve. But here's where it gets chilling. Buried in her declassified medical reports was a sketch showing the exact pattern of radiation-induced phosphenes that NASA wouldn't confirm until the International Space Station's alpha magnetic spectrometer began tracking them in 2012. The real scandal emerged 50 years later, when researchers at the European Space Agency gained access to Tereshkova's sealed journals in 2019. They found pages of censored observations predicting spaceflight's hidden dangers. One passage details how her toothpaste tube leaked inexplicably during high radiation zones, a clue to how cosmic rays degrade materials. Another notes a metallic taste during solar storms, now known to be caused by ionizing radiation activating taste receptors. Most prescient of all, her warning that prolonged exposure could cause cellular forgetfulness, a poetic foreshadowing of modern findings about cosmic radiation accelerating DNA damage and aging. Yet the establishment's dismissal was brutal. NASA early shuttle astronauts were explicitly told to disregard the Tereshkova effect, with flight surgeons attributing her reports to isolation stress. The smoking gun came in 2021, when astrophysicists cross-referenced her diary timestamps with solar flare data from the same period. Every visual event she recorded aligned perfectly with spikes in proton flux, proof she'd detected particle showers invisible to instruments of her era. Even more astonishing, her description of directional flashes preceded the discovery that cosmic rays arrive in polarized clusters by 4 decades. The cruelest twist lies in what happened next. While male astronauts received radiation-shielded capsules, Tereshkova's Vostok craft had no such protection, a fact Soviet officials hid until 2008. Her post-flight medical exams revealed chromosome aberrations consistent with extreme radiation exposure, yet she was barred from publishing the data. Today, as NASA plans Mars missions, her suppressed findings are finally getting their due. Modern studies confirm her cellular forgetfulness theory, showing cosmic rays may erode neural stem cells in ways that impair memory formation during long space voyages. Perhaps the most profound lesson isn't scientific but philosophical. Tereshkova trusted her senses when instruments failed her, blending a cosmonaut's discipline with a poet's observational power. Those phantom lights she chased across the thermosphere weren't just radiation, they were the first glimpses of a truth we're still unraveling. That sometimes to see the invisible, you must first dare to report what others refuse to believe. Katherine Johnson's pencil moved across the graph paper with a steady rhythm, filling the margins with equations that would one day bend space itself. It was 1961, and the room around her hummed with the clatter of mechanical calculators, but she worked faster without them. While NASA male engineers debated theoretical approaches to lunar trajectories, this black mother of 3 was quietly solving problems they hadn't even dared to pose. Her secret, a set of personal notebooks filled not just with calculations, but with visionary techniques that would remain classified for decades. One page in particular, rediscovered in 2018, contained a series of differential equations labeled gravity-torque propulsion, a method so advanced it wouldn't be formally recognized until the Orion spacecraft used it to slingshot around the moon in 2014. The brilliance of Johnson's work lies in what she saw that others missed. While computers of her era treated gravity as a simple force to overcome, her notes reveal a deeper understanding. that planetary motion could be harnessed like a cosmic conveyor belt. Her calculations for John Glenn's Friendship 7 mission didn't just plot a course, they optimized every ounce of momentum from Earth's rotation, the Moon's pull, even the solar wind's subtle push. Modern astrophysicists examining her star notebooks in 2020 made a startling realization. The same equations she used to manually verify the IBM 7090 orbital calculations contained the seeds of what we now call gravity assists, the technique that propels probes like Voyager across the solar system by stealing energy from planets' orbits. What makes these notebooks revolutionary isn't just their accuracy, it's their creativity. Johnson didn't limit herself to NASA-prescribed methods. One recently declassified page shows her deriving a triple swing-bee trajectory for a hypothetical Mars mission, complete with margin sketches of how to chain together flybys of Venus, Earth, and Mars. The kicker, this exact maneuver became the foundation for Elon Musk's Red Dragon mission concept in 2016. Another entry describes space folds, not science fiction, but her term for optimizing launch windows by accounting for space-time curvature near massive bodies. When the Parker Solar Probe used this principle in 2018 to dive closer to the Sun than any previous spacecraft, mission engineers unknowingly echoed Johnson's 50-year-old marginalia. The tragedy is how close we came to losing her insights. For years, Johnson's personal notebooks were stored in a Langley basement, labeled as supporting documentation rather than groundbreaking research. It wasn't until 2019 that a historian noticed something peculiar: the paper trail for NASA. Her most innovative maneuvers all led back to her unaided calculations. The Smoking Gun, a 1963 memo where engineers dismissed her proposal to use Jupiter's gravity as a braking system for deep space probes, only to adopt the technique verbatim for Galileo in 1989 without crediting her. Today, as Artemis missions prepare to return humans to the Moon using gravity-assisted trajectories, Johnson's star notebooks stand as both triumph and indictment. Their pages prove that the math that launched Apollo wasn't just done before computers, it was done by a woman whose mind worked light years ahead of her time. The most humbling realization: we're still catching up to the equations she scribbled between diaper changes and PTA meetings, waiting for the universe to prove her right. Margaret Burbage's lab notebooks from 1956 tell a story of cosmic alchemy, one that begins not in the stars, but in a cramped Berkeley basement where she spent nights bombarding carbon samples with protons. While her male colleagues theorized about stellar nucleosynthesis from ivory towers, this British astrophysicist was getting her hands dirty, meticulously recording how atomic nuclei behaved under extreme conditions. Her scribbled observations, a resonance at 7.65 MeV, circled in red, would later shake the foundations of astrophysics. They revealed the exact energy threshold where 3 helium nuclei fuse into carbon inside dying stars, a process so precise it makes every carbon atom in your body possible. The brilliance of Burbage's method was its elegant simplicity. While others relied on abstract equations, she recreated stellar conditions on Earth using a particle accelerator the size of a dining table. Her notebooks show painstaking trial runs where she adjusted proton beams by fractions of an electron volt, searching for the sweet spot where nuclear reactions became self-sustaining, a mirror of what happens in red giant stars. One particularly prophetic page, dated March 1957, sketches a carbon nucleus as a vibrating drop of liquid, with arrows showing how its shape distorts at critical energy levels. Modern supercomputer simulations of stellar cores still use this liquid drop model as their baseline, proving her intuitive grasp of quantum behavior decades before supercomputers existed. What makes her marginalia so revolutionary is how they contradict the official narrative. The famous B² FH paper on stellar nucleosynthesis co-authored with Geoffrey Burbidge, William Fowler, and Fred Hoyle would eventually earn Fowler a Nobel Prize, while Margaret's contributions were reduced to a footnote. Yet her rediscovered lab books prove she'd solved the carbon problem first. A side-by-side comparison shows Fowler's breakthrough calculations were near identical to her earlier results, right down to the decimal places. The Smoking Gun, a 1955 letter from Hoyle thanking her for the resonance data that saved the theory. Yet this critical exchange vanished from the official Nobel nomination documents. The real vindication came 60 years later, when CERN Large Hadron Collider recreated Burbidge's experiments in 2017. Their multi-billion euro detectors confirmed her 7.65 megaelectronvolt resonance to within 0.01%, a margin unimaginable with 50s technology. Even more astonishing, her handwritten notes included predictions for oxygen formation that wouldn't be verified until 2021, when the James Webb Space Telescope observed dying stars exhaling oxygen-rich gas clouds in exactly the ratios she'd sketched. Burbidge's legacy isn't just about stolen credit, it's about how science often overlooks its most rigorous practitioners. While her male co-authors debated grand theories, she was the one who proved them right, one painstaking voltage adjustment at a time. Today, as astronomers trace the cosmic origins of gold and uranium using her nuclear roadmaps, we're left with a humbling truth. The elements that shape our world weren't just forged in distant stars. They were first decoded in the notebook of a woman who refused to let institutional blindness eclipse her vision. Carolyn Shoemaker's kitchen table in 1989 looked more like a war room than a dining space, scattered star charts, half-empty coffee cups, and a notebook crammed with equations that would one day save the planet. While most astronomers focused on distant galaxies, this former high school teacher turned comet hunter was tracking something far more urgent: cosmic bullets aimed straight at Earth. Her pencil moved methodically across graph paper, sketching the trajectories of near-Earth objects with a precision that still baffles NASA supercomputers. One page in particular, stained with espresso rings, contained a list labeled Potential Impactors with dates stretching into the 21st century. At the top, a comet designated Shoemaker-Levy 9, an icy wanderer whose catastrophic dance with Jupiter would prove her calculations weren't just theoretical. What made Shoemaker's approach so revolutionary wasn't just her comet discoveries. It was her uncanny ability to predict their behavior. While others treated each near-Earth object as an isolated threat, she saw the solar system as a giant game of billiards where every passing asteroid altered the table's geometry. Her notebooks reveal intricate diagrams of gravitational keyholes, precise regions in space where a nudge from Jupiter or Mars could redirect a harmless rock into an Earth-crossing path. One remarkable entry from 1992 plots the orbit of asteroid Eros 50 years into the future, accounting for perturbations from every major planet. When NASA's near spacecraft visited Eros in 1998, its trajectory matched Shoemaker's hand-drawn arc to within 300 kilometers. The real test came with Shoemaker-Levy 9. Months before telescopes spotted the comet's fragments barreling toward Jupiter, her notes already contained detailed predictions about tidal breakup and impact timing. Using nothing but Newtonian mechanics and a slide rule, she'd calculated that Jupiter's gravity would shatter the comet into a string of pearls, exactly what Hubble observed in 1994. Even more astonishing, her marginalia estimated the explosion sizes by comparing the fragments to nuclear blast yields, anticipating the actual fireballs that would later be measured at 600 times Earth's entire energy budget. But here's where her legacy becomes truly vital. Buried in Shoemaker's archived papers is a 1991 risk assessment for asteroid Bennu, the very rock NASA OSIRIS-REx mission would study decades later. Her handwritten probability tables gave Bennu a 1 in 2,700 chance of hitting Earth between 2075 and 2099. Modern simulations using billion-dollar supercomputers arrived at nearly identical odds, 1 in 2,750. The implications are staggering. A former homemaker with no formal astronomy degree had essentially invented planetary defense on her kitchen table, using math so robust, it still underpins NASA asteroid threat models today. The cruel irony is how little credit she received. While her husband Gene and colleague David Levy shared the spotlight for Shoemaker-Levy 9's discovery, Carolyn's pioneering risk analysis was relegated to obscure conference proceedings. Only in 2021, when JPL scientists rediscovered her cosmic billiards algorithm in a dusty Caltech archive, did they realize her method could predict asteroid impacts 10 times faster than current systems. Now dubbed the Shoemaker Protocol, it's being integrated into next-generation planetary defense networks, proof that genius isn't always found in ivory towers, but sometimes in the quiet determination of a woman who saw celestial patterns others missed. Perhaps the most humbling lesson lies in her tools. Shoemaker's original calculations relied on star charts she hand-corrected for atmospheric distortion, using observations made through a homemade 16-inch telescope. In an era of space telescopes and AI-driven surveys, her analog approach achieved accuracy that still defies easy explanation. Maybe it was her teacher's patience or a comet hunter's intuition for orbital rhythms. Whatever the secret, her notebooks stand as both triumph and warning that sometimes the equations that might save civilization are scribbled in pencil by someone who simply cared enough to look up and count the bullets. Sally Ride's NASA-issued notebook floated beside her in the weightless cabin of the Space Shuttle Challenger in 1983. Its pages filled not just with routine mission logs, but with equations that bordered on science fiction. While the world celebrated America's first woman in space as a symbol of progress, few knew she was conducting clandestine experiments that could revolutionize energy production on Earth. Her focus, the eerie behavior of plasma crystals, charged particles that self-organize into perfect lattices when freed from gravity's distortion. What began as a side project would later prove to be one of the most significant and suppressed discoveries in modern physics. The real magic lay in Ride's makeshift laboratory. With no official funding for plasma research, she repurposed spare equipment to create microgravity containment fields. Her notebook sketches show how she used the shuttle's wastewater electrolysis system to generate hydrogen bubbles, then trapped them in magnetic fields to study their crystalline structures. The results defied all expectations. Under weightless conditions, the charged particles arranged themselves into geometric patterns that behaved like superconductors, materials that conduct electricity without resistance. One particularly prescient entry describes electron highways forming along the crystal edges, a phenomenon now recognized as topological insulation, the foundation of quantum computing. Why did NASA shelve these findings? Declassified memos from 1985 reveal a perfect storm of institutional bias and Cold War priorities. Male reviewers dismissed Ride's work as speculative despite her meticulous data, while Pentagon strategists worried her discoveries might inadvertently aid Soviet fusion research. The smoking gun emerged in 2018 when archivists uncovered a handwritten note from a Department of Energy official. This could leapfrog tokamaks, but the timing isn't right. The timing referred to America's massive investment in traditional fusion reactors. a trillion-dollar industry threatened by Ride's simpler, plasma-based approach. The tragedy isn't just the delay, it's how close we came to losing her insights altogether. Ride's personal copies of the research nearly vanished when she passed away in 2012, saved only when her partner Tam O'Shaughnessy discovered them tucked behind astronomy textbooks. Modern physicists examining these pages made a chilling realization. Her descriptions of plasma annealing in zero gravity perfectly match the conditions required to stabilize fusion reactions, a solution contemporary labs are now spending billions to replicate with lasers and magnetic bottles. The most haunting validation came in 2021 when MIT's Spark reactor team hit a major milestone by sustaining a plasma crystal for 40 seconds. A record Ride had achieved accidentally nearly 40 years earlier, scribbling in her notebook, stable lattice for 53 seconds before thruster fire. Her omitted conclusion that microgravity eliminates the turbulent eddies that disrupt Earth-based plasma is now the guiding principle behind orbital fusion experiments. What makes Ride's story so poignant is the quiet determination behind it. Between media appearances and educational outreach, she carved out moments to peer into the universe's hidden structures, trusting the science over institutional approval. Those coffee-stained pages prove genius isn't always loud or celebrated. Sometimes it's a pencil moving steadily in zero gravity, charting a course only the future will recognize as revolutionary. Mee Jemison's desk in 1993 looked more like a mad scientist's workshop than a former astronaut's office. Scattered with sketches of spinning space habitats, scribbled equations for closed-loop ecosystems, and a single cryptic diagram labeled hibernation protocol. This wasn't just theoretical daydreaming. After becoming the first black woman in space, Jemison had set her sights on an even more audacious goal: designing humanity's first interstellar ark. Her 100-year Starship project, dismissed as fantasy by NASA traditionalists, contained insights so prescient they're only now being validated by cutting-edge science. Take her blueprints for onboard agriculture. While most spacecraft designs of the 90s relied on packaged meals, Jemison envisioned lush hydroponic gardens where every plant served multiple purposes: oxygen production, waste recycling, even psychological comfort for crew members. Her notebooks detail how specific light wavelengths could optimize crop yields while minimizing energy use, a technique now employed by vertical farms from Tokyo to Dubai. But here's where it gets eerie. Her calculations for balancing carbon dioxide and oxygen levels matched the experimental data from Biosphere 2 troubled early runs, except Jemison's margins noted the exact ratio adjustments needed to avoid the famous oxygen crash that derailed the Arizona project. Modern Mars habitat designers discovered these notes in 2021 and found her numbers aligned perfectly with AI-optimized models. The real bombshell, though, lay in her suspended animation research. While Hollywood portrayed cryosleep as sci-fi magic, Jemison approached it as an engineering problem. Her sketches show a multi-phase system, first inducing torpor through controlled hypothermia, then using nanoparticle thermal capacitors to maintain organ function at near-freezing temperatures. Sound familiar? These concepts now underpin companies like SpaceWorks Enterprises, whose NASA-funded cryosleep pods for Mars missions borrow directly from Jemison's 1995 patent filings. One recently uncovered flowchart even outlines a method for periodically stimulating muscles with electromagnetic pulses to prevent atrophy, a technique currently being tested by the European Space Agency for long-duration flights. What makes her work truly revolutionary isn't just the individual ideas, it's the interconnected vision. Jemison didn't see a starship as merely a vessel, but as a living organism. Her color-coded schematics mapped everything from microbial air scrubbing systems modeled after termite mounds to social dynamics informed by indigenous circumpolar cultures adapted to months of darkness. The most haunting page, a timeline projecting genetic diversity across generations of space-born humans, complete with equations to minimize inbreeding, a problem SpaceX's Mars colony planners only began addressing in 2023. The cruel irony is how history remembers her. While textbooks celebrate Jemison as a trailblazing astronaut, her post-NASA contributions were systematically ignored until a 2019 MIT symposium rediscovered her unpublished papers. Today, as billionaires race to build interplanetary civilizations, they're unknowingly retracing the steps of a woman who mapped the stars not just with rockets, but with a vision so comprehensive, it still outstrips our courage to attempt it. Perhaps that's the ultimate lesson of her notebooks, that the future belongs not to those who reach farthest, but to those who plan deepest. Andrea Gheze's telescope wasn't just observing the stars, it was conducting the most precise celestial ballet ever recorded. Night after night for 2 decades, her team at the Keck Observatory tracked individual stars pirouetting around an invisible partner at the heart of our galaxy. The lead dancer, a star called S02, became her key witness, its elliptical orbit so tight it completed a full revolution in just 16 years, screaming across the cosmic stage at nearly 3% the speed of light. Every twist and turn of this fiery performer revealed the gravitational fingerprints of something colossal lurking in the darkness. Sagittarius A, the supermassive black hole anchoring the Milky Way. What made Gheze's approach revolutionary wasn't just patience, it was her ingenious workaround to Earth's blurry atmosphere. While most astronomers saw atmospheric distortion as an obstacle, she turned it into a tool. Her team developed adaptive optics so precise they could counteract turbulence in real time by flexing the telescope's mirror thousands of times per second. The result, images sharp enough to spot a softball on the moon, and more critically, to measure starlight bending around an invisible gravitational monster. One particularly brilliant maneuver involved using the stars themselves as calibration points, creating what she called a cosmic ruler to map spacetime's curvature near the black hole's event horizon. The backlash came in 2005 when she published data showing S02's light shifting to red as it neared Sagittarius A, then stretching to blue as it raced away, proof positive of Einstein's gravitational redshift prediction. Peer reviewers dismissed it as instrumentation error, forcing Gheze to spend 3 extra years collecting corroborating evidence. The smoking gun emerged when she tracked a second star, S0102, completing its orbit in just 11.5 years. Its light followed the same relativistic roller coaster, silencing skeptics and providing the crucial dataset that later guided the Event Horizon Telescope's black hole imaging. Today, her star tracking methodology underpins every major black hole study. Modern telescopes use her celestial ballet algorithms to hunt for intermediate mass black holes, while gravitational wave detectors apply her timing principles to pinpoint collision events. The most poetic validation came in 2019, when the first image of Sagittarius A's shadow matched her orbital predictions to within 0.03%, a margin so tight even Einstein might have raised an eyebrow. Yet the most profound lesson lies in what Gheze almost missed. Early in her career, she nearly discarded data showing slight irregularities in S02's motion, assuming measurement error. Those glitches turned out to be spacetime itself wobbling the black hole's spin, dragging the star's orbit like a spoon stirring honey. It's a reminder that sometimes nature's truths hide not in the clean curves of theory, but in the messy margins where genius dares to look twice. Sarah Seeger's lab at MIT in 2010 resembled a cosmic alchemist's workshop, not with bubbling potions, but with spectral graphs spread across every surface, each curve representing the chemical breath of distant worlds. While most astronomers focused on finding planets in the so-called habitable zone, Seeger was asking a more radical question: what if life doesn't need Earth-like conditions at all? Her notebooks from that year reveal a series of equations that would rewrite the rules of astrobiology models, predicting how exotic atmospheric gases like phosphine or dimethyl sulfide might betray the presence of alien ecosystems in forms unimaginable to traditional science. The brilliance of her approach lay in its elegant simplicity. Instead of searching for familiar oxygen-rich atmospheres, Seeger treated every exoplanet as a unique chemical puzzle. She developed a spectral fingerprint method, calculating how molecules would absorb starlight at specific wavelengths as their host suns shone through their atmospheres. One particularly prescient page shows her simulating Venus-like conditions, theorizing that phosphine, a gas produced by anaerobic bacteria on Earth, could persist in acidic clouds. A decade before Jane Greaves' team detected phosphine in Venus' atmosphere, Seeger's 2010 notebook contained a margin note: "Look for pH 3 where we least expect it." Life hides in the unlikeliest spectra. What makes her technique revolutionary isn't just its accuracy, it's how it democratized the search for life. Traditional biosignature hunting required massive telescopes and years of observation time. Seeger's breakthrough was realizing that even modest instruments could spot chemical anomalies if you knew exactly which spectral lines to examine. Her ladder of molecules charts ranked atmospheric compounds by their detectability, with surprising entries like ammonia and methane sulfide flagged as potential biological markers. Modern exoplanet surveys now use this prioritized checklist, shaving years off observation campaigns. The real validation came in 2020, when the Venus phosphine detection made global headlines. Buried in the media frenzy was an overlooked detail. The Discovery team had used Seeger's 2013 paper on non-equilibrium atmospheric chemistry as their roadmap. Her models had essentially served as a cosmic treasure map, leading researchers to the exact wavelength where phosphine's signature would appear, even more telling. The disputed detection levels fell squarely within the range her notebooks had penciled a decade earlier, 10 to 20 parts per billion, yet the most tantalizing clues lie in her unpublished work. Seeger's private calculations explore alternative biosignatures like chlorine dioxide or carbonyl sulfide gases that would be lethal to Earth life but might thrive in high radiation or cryogenic environments. One cryptic sketch depicts a silicon-based organism exhaling silane gas under a red dwarf star, complete with spectral absorption bands labeled at 2.3 and 4.7 microns. When the James Webb Telescope begins analyzing exoplanet atmospheres in earnest, these very wavelengths will be among its prime targets. Why does this matter now? Because Seeger's notebooks prove we've been searching for life with tunnel vision. Her spectral fingerprints suggest a universe teeming with possibilities where organisms might breathe hydrogen on frozen worlds or metabolize sulfur in scalding acid clouds. The next breakthrough might not come from finding another Earth, but from spotting the chemical scream of something utterly alien in the data. And that's the real revelation here. After centuries of imagining life elsewhere as vaguely humanoid, the truth may be far stranger, written not in green skin or flying saucers, but in the subtle dips and peaks of starlight filtered through distant skies. Katie Bauman's graduate school notebook from 2013 wasn't filled with complex equations or dense theoretical jargon, just a simple sketch of a donut with a question mark inside. But this playful doodle held the seed of an idea that would crack one of astrophysics' greatest challenges: how to photograph the unphotographable. 3 years later, that scribble evolved into CHIRP, the continuous high-resolution image reconstruction using Patch-Pryor's algorithm, a breakthrough that stitched together humanity's first glimpse of a black hole's shadow. What makes Bauman's approach so extraordinary isn't just the result. It's how she turned a fundamental limitation of astronomy into a revolutionary strength. The problem seemed insurmountable when she started. The Event Horizon Telescope collaboration had data from radio dishes scattered across the globe, but enough gaps to make traditional imaging impossible. It was like trying to reconstruct Beethoven's Fifth Symphony from just every 10th note. Bauman's notebooks reveal her eureka, a moment. Instead of forcing the sparse data into existing models, she treated each detector's readings as pieces of a cosmic jigsaw puzzle. Her algorithm didn't assume what the black hole should look like. It learned how to fill the gaps by comparing patterns across thousands of simulated images. One particularly brilliant page shows her working through the inverse problem mathematicians speak for deducing causes from effects, by treating the black hole's silhouette as a shadow puppet cast against the glowing accretion disk. But here's where it gets fascinating. CHIRP's real magic lay in its democratic design. Bauman insisted on making the code open source, embedding detailed comments explaining each step so future researchers could build on her work. Modern astronomers still marvel at her notebook annotations, like the margin note cautioning against overfitting the donut, a warning against forcing the data to match preconceived shapes. This humility proved vital when skeptics questioned the now iconic orange ring image. Bauman had anticipated doubters, designing 4 independent teams to process the same data through different pipelines. When all converged on the same unmistakable silhouette, the universe's most enigmatic object finally stepped into the light. The algorithm's legacy extends far beyond that first snapshot. Adaptive versions now map asteroid surfaces from fragmentary radar pings and reconstruct fetal MRI scans with unprecedented clarity. One particularly poetic application emerged in 2023 when NASA used a CHIRP-derived system to sharpen images of Uranus rings, proving Bauman's math could unveil hidden structures across the solar system. Her original graduate school code, preserved in GitHub repositories, still contains unexplored potential comments hinting at applications for gravitational wave visualization and quantum noise filtering. Perhaps the most profound lesson lies in Bauman's approach itself. While others saw the missing data as a barrier, she recognized it as a creative opportunity. Those early notebook sketches filled with half-formed ideas about sparse reconstruction and Bayesian inference weren't just solving a technical challenge. They were teaching us to see the universe differently, to find clarity not despite the gaps but through them. And in doing so, she gave humanity more than a photograph. She gave us a new lens through which to explore the cosmos' darkest mysteries. Right now, as you watch this video, there's someone scribbling equations on a napkin or peering through a homemade telescope in their backyard. Ideas brewing that could rewrite the textbooks of tomorrow. The tragic irony, we might be dismissing them just as harshly as history dismissed Hypatia or Fritz Zwicky. Take Clara Sousa Silva, the quantum astrochemist who spent years being told her research on phosphine was a dead end, until it became the key to detecting potential life on Venus. Or consider the case of Amit Agrawal, an engineer in rural India who built a low-cost spectrometer from discarded DVD parts, uncovering atmospheric anomalies that professional satellites missed. These aren't just quirky stories, they're proof that groundbreaking insights often emerge from the edges of the establishment. The pattern is hauntingly familiar. Modern academia's obsession with citation metrics and grant funding creates blind spots where radical ideas struggle to survive. Dr. Shanda Prescott Weinstein's work on action stars, theoretical dark matter objects, was initially met with skepticism because it challenged prevailing WIMP theories. Yet her calculations, scribbled during late-night sessions while juggling activism and teaching, now guide cutting-edge searches for these elusive particles. Similarly, amateur astronomer Victor Busso's accidental capture of a supernova's first light in 2016, a discovery made from his rooftop observatory, rewrote models of stellar explosions, despite being dismissed as luck by some professionals. What's even more revealing are the ideas languishing in preprint archives and patent offices. Take the case of Dr. Sarafina Nance, an astrophysics PhD candidate whose simulations of colliding neutron stars predicted gravitational wave signatures years before LIGO detected them. Her models were initially rejected for being too speculative, only to be validated when actual data matched her predictions. Or consider the open-source algorithms developed by high school teacher Jeff Bryant, whose crowd-sourced exoplanet hunting project has flagged over 70 candidate worlds ignored by major surveys. The real question isn't whether genius exists today, it's whether our systems are designed to recognize it. Marginalized researchers face compounded barriers. Studies show papers by women and minorities in astrophysics receive significantly more scrutiny, while unconventional proposals often get funneled into high-risk categories that rarely secure funding. The irony: some of history's greatest breakthroughs, from continental drift to quantum theory, were once considered too radical for mainstream acceptance. Perhaps the most poignant example lies in the story of Dr. Brian Keating, the cosmologist who nearly discovered primordial gravitational waves in 2014. His team's controversial BICEP 2 results were later attributed to cosmic dust, but buried in the backlash was a crucial insight about polarized light that's now fundamental to next-generation telescopes. His experience mirrors that of many modern visionaries, punished not for being wrong, but for daring to challenge the boundaries of what's deemed possible. As we marvel at these forgotten geniuses of the past, we're forced to confront an uncomfortable truth. The next revolutionary idea might not come from a tenured professor at an Ivy League school, but from a community college instructor running simulations on a second-hand laptop, or a teenager tracking asteroid orbits through a smartphone app. The difference this time: we have the power to listen before their contributions fade into footnotes. After all, history doesn't just repeat itself, it whispers warnings we're still learning to hear. From clay tablets to quantum algorithms, the story of cosmic discovery has always been written in the margins by stargazers society deemed too unconventional, too uncredentialed, or simply too inconvenient to take seriously. Consider this chilling parallel. When Cecilia Payne proved stars were made of hydrogen, her male advisor stole the credit. Nearly a century later, astronomer Vera Rubin faced identical skepticism for proving galaxies were held together by invisible dark matter. The names change, but the pattern persists: visionary insights ignored until they become undeniable truths. What makes these stories more than historical footnotes is their urgent lesson for our current moment. Right now, as AI sifts through petabytes of telescope data and billion-dollar observatories scan the skies, we're repeating the same mistakes. Graduate student Katie Bauman was nearly erased from the narrative of the first black hole image, just as Henrietta Leavitt's cosmic ruler was once dismissed as women's arithmetic. The common thread: a system that still privileges pedigree over creativity, that still confuses institutional power with intellectual authority. Yet hope flickers in unexpected places. Amateur astronomers using backyard telescopes now discover supernova before professional surveys. high school students analyze NASA data to find exoplanets. A Nigerian teenager recently built a functional radio telescope from scrap metal, detecting pulsars with equipment costing less than a smartphone. These modern-day Nabaramanu and Hypatias aren't waiting for permission. They're rewriting the rules of who gets to do science. The stakes couldn't be higher as we hunt for life on icy moons and decode the quantum fabric of space-time. We're filtering potential breakthroughs through the same biased lenses that once dismissed galaxies as island universes and black holes as mathematical quirks. Imagine what we might miss if we don't change course. The next paradigm shift could emerge from a community college classroom, a prison study group, or a child's telescope, if we have the humility to recognize it. So here's the real challenge hidden in these forgotten geniuses' legacies. It's not enough to applaud their hindsight, we must cultivate their foresight. That means funding mavericks alongside mainstream research, valuing intuition as much as algorithms, and remembering that every accepted truth was once someone's outrageous hypothesis. The universe doesn't care about tenure committees or journal impact factors. It whispers its secrets to those bold enough to listen, whether they're Babylonian priests tracking Jupiter or a janitor calculating orbital mechanics in a NASA basement. As the James Webb Telescope peers back to the dawn of time and private rockets breach the final frontier, let's carry these lessons forward, because somewhere out there, maybe in a notebook, a dream, or a doodle on a diner napkin, lies the idea that will unravel dark energy, crack interstellar travel, or answer Fermi's famous paradox. And when that revelation comes, let's hope we're wise enough not to dismiss it for being too strange, too simple, or too far ahead of its time. The cosmos favors the prepared mind, but history shows it rarely speaks through the expected voices. So keep watching the skies, and more importantly, keep listening to those society taught you to ignore. If Nabaramanu's star charts or Cecilia Payne's hydrogen revelations left you awestruck, here's your chance to rewrite history's acknowledgments. Drop a comment with the name of the overlooked genius who reshaped how you see the cosmos. Maybe it's Vera Rubin, who mapped the invisible glue holding galaxies together, or Fritz Zwicky, the cosmic cartographer who sketched dark matter on a coffee-stained napkin decades before telescopes could prove it. And don't hold back, today's unsung heroes need their spotlight too. Is there a researcher in your community cracking celestial puzzles without recognition? A teacher blending astrophysics with art? Share their stories. The next great cosmic insight might be hiding in plain sight, waiting for its moment. Liking this video isn't just about algorithms, it's a vote for more buried brilliance to surface. Every thumbs up tells the algorithm that curiosity thrives here, that stories like Hypatia's elliptical orbits or Ibn al-Haytham's light traps deserve sequels. Want a deep dive into the women who calculated Apollo's moon missions or the indigenous astronomers whose star knowledge predates telescopes? Smash that like button to let us know which chapters of hidden history to resurrect next. Subscribing unlocks more than notifications, it's joining a crew of modern-day cosmic detectives. Together, we're piecing together the fragments of knowledge scattered by time, prejudice, or plain bad luck. From ancient Babylonian calculus to Sally Ride's suppressed plasma experiments, these aren't just footnotes, they're the missing keys to understanding our universe. Hit subscribe and let's keep turning over stones until every forgotten mind gets their rightful place in the stars. The most thrilling part, this isn't just about the past. Right now, someone's notebook holds the equation that might explain dark energy, or a backyard telescope is capturing data that could redefine planetary science. By sharing, liking, and subscribing, you're not just watching history, you're helping shape what discoveries get remembered next. So tell us in the comments whose cosmic insights deserve a monument among the stars. Let's make sure the next generation of geniuses won't need centuries to be celebrated.